So I guess we can get started. Um, so today, hello guys. So I guess we can get started. And today I'm going to go through some of the calculations that was frequently asked by the previous students, and also some of the miscellaneous. Did I read it correctly? Miscellaneous. Okay. So first, I would like to talk about the calculation about the significant figures. So there are some definitions, but I'm not going to read it. I'm just going to go through some of the rules, like examples. So we can see for the first case, for the addition. So for this one, we know it has 4 significant figures, and this one it only has 3. So if we do the addition, we will have this one. In this case, for the addition, this has 1 digit after the decimal point. This has 2 digits after decimal point. So in this case, we only keep 1 digit. So we will report this value. And for the subtraction, it is the same. So this one has 1 digit after decimal point, and this one has 2 digits after decimal point. When we do the calculation, we can keep 2 digits, but when we are reporting the data, the standard way is to only report only 1 digit after decimal point. So in your calculations, in the assignment, you may use these rules. And the third one is about multiplication. And in this case, we can see that we keep the least significant figures. So we don't care about the decimal points. We care about the significant figures. This one, it has 4 significant figures, but this one, it only has 3. So the maximum precision will be 3. So we can do the multiplication by using these 2 numbers. But when we are reporting data, we will make it have 3 significant figures. And this is the same for division. So this one has 3 significant figures. So when we report data, we only report 3 significant figures. And the rules is are here. And if you're interested, you can read this. And I will upload these slides on ENCE. And so for here, do you guys have any questions? Yes.
Just in regard to rounding up versus rounding down, is there a consistent thing that we should do, or should we?
What do you
like? If it's 163, round down.
163.
But 63 we rounded down to 6, but 77 rounded up to 8. Should we always just go with the closer number, or should we always round down or always round
like
down?
If it is 4, and then we round it to 0, and then we ignore it. It is 5, we plus 1 to the previous digit. Yes. Any more questions? Actually, when I was young, I had another question like, if I have a log, 1, 3, 1, blah, blah, how do I report? But it didn't tell us. So I'm not sure now, but I don't think we will use it. But if we meet the log or the exponential, I will suggest we use this method. So when we get the results, we report the number with the least significant figures. Yes?
Do you prefer, if we're doing like a multi-step problem, to continuously round after like each step, or should we keep like the long number and then at the very end just round it?
Oh yeah, this is a good question. So in the calculation, we will keep like something like this. Like during the process, we will keep this because when we are doing the rounding will generate errors. So we just keep the like many decimal points, and after the final result, we round the final result. And actually, this process happens in the computer science because the computer can only remember a limited number of the digits. So if we have a large calculation, the computer will accumulate this error. So they have some algorithm to solve that problem. So the next one, I would like to talk about error propagation equations. So first, I think we are familiar with this Pythagoras theorem. And we can see square of C equals to the square of A plus square of B. And actually, the error propagation is similar to this case. We can see that if we have the data like y equals to x1 plus x2, or y equals to x1 minus x2, and x1, delta x1 is the error of x1, and delta x2 is the error of x2, and delta y is the error of y. And we can see that they satisfy this relation, like the square of delta y equals to the sum of square of delta x1 plus sum plus delta of x2, the square of delta x2. So basically I call this triangle of absolute errors. But note that the coefficient here is 1. If this is like y equals to ax1 plus bx2, then this triangle will be a square delta x1, or we can do something like this. And this is bx2 square, and this is delta y square. So this is for absolute error. And similarly, we have the triangle of relative errors. And relative errors is a case for multiplication and division. So they are the same. And again, the coefficients are 1. And we can see the relative error of x1 and the relative error of x2. If we plus them together, if we take the square and plus them together, we can get the square of relative error of y. And then we can calculate, if we know the value of y, we can calculate the absolute error of y. So I think this is more intuitive than the error propagation tables. Yes.
So what value are we interested in? Are we looking for delta y? Is that what we are solving for?
Yes.
Okay.
Like for some cases, we are interested in the absolute error. Like when we are reporting data, we may have like the concentration of calcium equals to 10 plus minus 5. So we may be interested in the absolute value, absolute error. But sometimes we are interested in the relative error. And for now, I don't have any cases, but maybe in future we can meet this problem. Okay. And by familiar with this, let's see this example. So this example that's shown in the slide, in the lecture slide, we can see we are diluting a wastewater sample for further analysis. And first, we add 10 mL plus minus, this is the error of wastewater sample, into a beaker. And then we add another volume of DI water into the beaker. So we have a mixture of wastewater and DI water. I think you guys may do this experiment in a previous class, like the solid lab. And for question 1, the question is what if, actually this is what is. What is the absolute error and relative error of the mixture? And so in this case, there should be like the volume, like what's the absolute error and relative error of the volume of the mixture. So in this case, we have V1 equals to 10 plus 0.02 ml, and V2 equals to 25 plus minus 0.03 ml. And the total volume equals to V1 plus V2. So this is the summation. So we know that the delta V1, this is delta V2, and this is delta sigma V, and we have this relation. So in this case, we can calculate the total volume equals to V1 plus V2, and the absolute error of V1 square is equals to the sum of square of its components. So we have this one, and then we can solve this equation, and then we can have this one. So this is the absolute error of the total volume. And we can also calculate the relative error by using the absolute error divided by the total volume, and this is the relative error of the total volume. We can see that the relative error is kind of the absolute error is larger than any of its components. And then for the second question, now you plan to add 5 milligram of sodium chloride into the mixture, and the measurement error of the balance is this one. And the question is, what is the absolute error and relative error of the sodium chloride concentration? And in this case, we know that the concentration equals to mass divided by volume. So this is a division question. And in this case, we know that according to the triangle, we can see the relative error of the concentration equals to, like they have these geometric relations. And in this case, the concentration can be calculated. So this is the mass of the NaCl, and this is the total volume. And then we can calculate the concentration. Here I just do the unit conversion into microgram per liter. And then we know the concentration, and we know the relative error of the volume that we have already calculated. Now we want to know this part, the relative error of the mass. And we know the absolute error of mass is this one. And we know the mass is 5. And then we can calculate the relative error of the mass. So we know everything except for delta C. So we can just plug the numbers into this equation, and we can get the relative error of concentration is 2%. And here I want to show that we can say the relative error of concentration is this one. This is a little bit very slightly greater than this one. So this is the relative error of the mass, and this is the relative error of the volume. We can see that if we have 2 components, and the relative error of one component is substantially greater than this one, we can see this is pretty small relative to this one. If this is substantially greater than that one, then the result is almost equal to the one that has a greater error. So basically, the one that has smaller error could be ignored. But for you guys in the calculation, you guys need to calculate all of the steps to make sure we got the correct result. And by having this one, we can calculate the absolute error of the concentration. And this is the absolute error. So for this one, do you guys have any questions? No? Okay. The next thing I want to talk about is linear regression. Here I just also provide a table about the terminologies of this regression, and we can see we have so many kinds of names. So you guys can choose which one you like. But I think we usually say by like independent, dependent, and independent. And here shows the equations that I show on Tuesday, which is a little bit complicated. So the general idea is that we want to know the uncertainty of the parameters because uncertainty are important. And we also want to know the uncertainty of our predictions. So in order to do the calculation, we need to know like this one. So there should be X bar and Y bar. So we need to know the average of this those two data. And we need also to calculate the sum of square of X, Y, and X, of X and Y and XY. And after that, we can calculate the coefficient B hat and A hat based on SXY and SXX. And after that, we can also use plug this in to calculate EI, because in this equation, if we know A, B, and X, Y, and YI, we can calculate EI. By having EI, we can use this equation to calculate sigma hat square. And by knowing the sigma hat square, because this is an estimate of sigma, so we can plug this in, we can calculate the variance of B hat and the variance of A hat. We do not care about this. And then we can use these values to calculate the predictions. So we have two predictions. The first one is the mean response. The second one is predicted response. The difference is that, so suppose we have a calibration curve, and this is our regression line. And then we will have one x0, like if I use the 10 microgram per liter NaCl concentration, I want to measure this. So I have one concentration input, so I can have one output, and this one output may have its errors. So this is supposed to have one result. But for other times, like I have plenty of this solution, or I measure it for many times. We know that if we measure it for many times, we can get an average predicted value. And for that average predicted value, this should be Y bar. So this is the average of the many input. And we can see that this one is greater than this one, because the difference is we have a 1 here. So it tells us that if we take many times, if we measure the sample for many times, the uncertainty can be decreased. But in practice, we usually only have one sample, so we are more caring about this one. Oops. So here shows the more colorful steps. So I just repeat that because it has steps. So first, we can calculate X bar and Y bar. And based on X bar and Y bar, we can calculate SXX and SYY, and also SXY. And by having that, we can calculate B hat and A hat based on SXY and XX. And by knowing A and B, we can plug it in the linear regression equation to calculate eta. By knowing the eta, we can come to calculate this sigma. And by knowing the sigma, we can calculate the variance of B and the variance of A. Oh, the color is not obvious from the projector, but when it's displayed in the screen, I think the color will be more saturated. Okay, anyway, and then we have a new data, like x new equals to x1. And based on all of these results, we can calculate this and this. And in the calculation, we are more about this. And in the homework, it's usually we are going to calculate this one. And by knowing the steps, Yeah, so finally we can get this one. So by knowing the steps, we can write the Excel. We can write these steps in the Excel, and this is an example. As I mentioned before, first we can calculate the average of x and the average of xy, and we can use the Excel function. After that, we want to calculate sxx, syy, and sxy by doing the calculation like this. So I use two steps. The first one, I use xy minus x bar, and then I take the square. And you guys may just only write it into one step. And similarly, we can calculate yi minus y bar, and then take the square. And then we make the summation, we can get syy. And similarly, we can calculate x minus x bar and y minus y bar, because Excel cannot input those mathematical symbols. So I just simplify this. And then we can calculate each of them and take the sum. By knowing xy and xyy, we can calculate a and b. So this is a calculation by myself, and this is the calculation like the auto-generated regression coefficient. We can see that they are equal. They are equal, yes. And then by knowing a and b, we can calculate y hat and y minus y hat. And similarly, we can take the square, and we can also have the xi square. By knowing this, we can get eta. By knowing the eta, we can get the s. By the way, I also want to mention that the degree of freedom and the sample size, they are also needed in the calculation, but these are lower at first, because when we count the data, we know the degree of freedom and we know the sample size. And by knowing this, we can calculate the variance of A and B. And then by knowing the new data x equals to x0, we can plug this into the regression equation to get y0 hat. And we can also calculate the uncertainty of y0 hat. So these are all the steps. And I suggest you guys can, because the data is here and I believe I'm correct. So you guys may use the Excel, use the same data to see if you guys can rebuild this table. If the calculations are correct, it means your steps should also be correct. Yes?
So this is a question about significant figures that I just remembered because I saw the counted numbers for the cone. Counted numbers that only have one significant figure, if we add or multiply or do any operation with those, do those affect the number of significant figures that we are allowed to use?
You mean in the Excel?
Well, just in any context, but like if you have two of something and the quantity of that thing is involved in your calculation, does that change the number of significant figures you can use?
Oh, that's a good question.
Or is it only for measurements?
I think the count does not, because it is not a measurement.
Okay.
Yes.
Thank you.
And also, you also mentioned a significant figure. So in this calculation, I didn't care about significant figures because it doesn't matter during the calculation, but when I report the data, say if I report this one, I will round this to the correct significant figures. So do you guys have more questions? Okay. Yeah, so this is a summary of the class. So first one, when we're reporting data, we need to pay attention to significant figures, yes. And in environmental science, the significant figures are usually, I didn't talk about this, but I want to say the significant are usually 3. So we will have like this one or this one. The reason that I think, because if we have 3 significant figures, and so the last one will have the 100, last one, like this influence. So the influence is small enough, but if you have a context, you should follow the rules given by the context. And the second one is source of errors includes, we have 4 sources. Do you guys remember?
The method of measurement, the instrument, and then the actual object.
Yes. Observer, method, instrument, and the object. And for the types of errors, it includes 3. Which 3 do you guys remember? Yes.
Random error, systematic error, and gross error.
Yes. Random, systematic. Yeah, I think my handwriting is still bad. And gross error. And then for the error propagation equation, if y equals to this one, so delta y equals to u.
Delta x1 squared plus delta x2 squared.
Really? We need to take the square root. Right?
Oh,
Yeah.
not squared, yeah.
And then for the subtraction, they are the same. So delta x1 square plus delta x2 square, and then we take the square root. And for the multiplication, and yes, delta x1 plus delta x2, and we take square and the square roots. And this is the same. Oh, if it's too small, next time I will make it larger. So, if 0 is inside or outside the confidence interval, they are significantly different. Do you guys remember?
Outside?
Outside, yes. And here I add a quote. I add a quote means, and it only applies for the t-test that we discussed. If it is in other tests, it may be different. So the significance level alpha is usually set to
0.05?
yes, 0.05. And then what can be used to identify potential outlier? Box plots, yes. Oh, like this Mac is very sleepy. Sometimes it will just go sleep. And I said the battery, when using battery, the display will turn off at 1 hour, but it's only turned off at 20 minutes. So it's very sleepy. Yeah, box plots. And what is usually used for outlier test when n is greater than 25 with normal distributed sample. I just show it once, so I'm not sure if you guys remember that. So this is grossness test. So this is a table provided by EPA. And I think in the future, when you guys are at work or doing research, this test is the most commonly used one. And the last one, error terms in linear regression usually follows a what distribution? Normal? Yes. Follows a normal distribution with its mean equals to 0, yes. So the error is like this. And so it is almost end, but I would like to talk more about the homework. So some of the frequently asked questions. So the first one is, like I have 2 balances to use. Like for example, here we have 2 balances. And the question is, which balance or pipettes I need to use? So the rule is that we use the one with capacity that is just greater than what we need, so that we can make sure we can minimize the errors. And another question is, what if I deliver it twice? For example, or n times. For example, I want to have a 100 ml DI water. And we have a couple of methods. For example, let's just say I use glass pipette. I can use this very small glass pipette and do it 200 times, right? And I guess no one will do that. And then I can use 1 ml pipette, do it 100 times. And I can use the 100 pipette to do it only once. Do you guys think will it make a difference? Like if I do this for 200 times and do this for one time, will it make a difference?
Yes.
What's the difference will be?
Error.
Error?
Error. The more times you do it, the more likely you are to make a mistake somewhere.
Yes. So that's the point. So ideally, we want to deliver the sample as less time as possible to minimize the error. And here is an example. If we deliver it twice, and for example, we know that the total volume equals to V1 plus V2, and according to the absolute error triangle, we have this relation. And let's just assume V1 equals to V2. So like 50 plus 50 equals to 100. So let's just deliver it for twice and use the same pipette. We can see that this one equals to 2 times delta V square. And we can see that the total error of the V does not equals to 2 times each one, because the coefficient is 2 if we take the square root. So basically, if we do it twice with the same equipment, the error will not double. It will increase by the factor of this one. So it's kind of like this is 1, 1, this is 2. So for this example, do you guys have any questions? So I think this is a little bit counterintuitive because the error does not double, but it increase, follows the rule of the triangle. So you guys are good? That's good. And I also want to say, this does not double. We can just imagine, like if we have a data, and it can be positive or it can be negative, like for the errors. And for another data, it can also be positive or negatives. So if we combine them together, the negative error and the positive error, they may be cancelled out. So the total error may not be that large. Another question about problem A, like how to calculate total solids. I think if you guys have done the solids lab, then you guys should be familiar with it. So it equals to the mass of the residue after 103 baking. And this is a volume of the sample. And the note here, like the delta M, like the error of the mass and the error of the volume can be found in the appendix table. So you need to figure out what equipment you will use to do the transfer, and then you find the corresponding errors, and then you use this in the calculation. Another question is, another thing I want to talk about is problem B. Problem B is about the ICP, like the induced coupled plasma emission. I will talk about this in the heavy mental lecture. So this is a diagram of ICP. So basically we have 3 inflows. Like A is a cooling gas because we want to decrease the temperature of our sample. And B is a discharge gas flow. And the C is a flow of the sample. So this is our sample. We just get into here. And this is a very strong magnetic field. And during this, our sample will become plasma. And it will be, so this will be some light. And then it will eject the light or electromagnetic wave. And then we will have a receptor here. And when we get the receptor, we will have the signal, like this signal. So I think here shows the signal strength. So when we talk about the ICP signal, we can consider the signal as a unitless value. So we don't care about its unit. So for this one, do you guys have more questions? No? And I think this is the last slide. Oh yes, and just again, we have due of assignment 1, 2, and quizzes. And on next Thursday, we are going to have lecture 4, which is very chemistry. So that's it. So if you have questions, yes.
So for assignment 1, what exactly are you expecting us to write? Do you want like a reflection on like each problem, or do you want a reflection on like the assignment and
On the assignment whole, like you can state, I have a hard time with what question, and I cannot understand maybe what question or what theory, and then you can let me know. So during the future class, I can adjust the content accordingly. Yes.
But you don't actually want all of our work for every single problem turned in, right?
Excuse me?
You don't want all of our work for all the problems turned in?
No,
You're
I
giving
don't.
us the solutions.
Yeah, I don't need your solutions for the questions. I need you write a summary of your assignment. Yes. If you don't have questions, you can leave here.